Imagine handing the keys to, I don't know, the entire national power grid over to an AI. And this AI is, it's a certified, unquestionable genius at mathematics.
Right.
But is entirely incapable of understanding what happens when a single critical wire gets crossed in a storm.
Yeah, that's the nightmare scenario.
It is. I mean, think about that for a second. We are rushing to give complex systems, our hospitals, our financial markets, logistics networks, over to machines that can, ace a bar exam in a few seconds.
Exactly.
But they might completely lack the ability to comprehend the domino effect of their own actions. And that is, frankly, the terrifying blind spot of modern tech right now. So today we are digging into a massive stack of documentation that claims to actually have the cure for this.
It's arguably the most critical blind spot in the entire industry right now. I mean, without a doubt. We spent the last decade obsessing over what a machine knows, right? Its trivia recall, its ability to generate a really polite email. But we are hitting a wall. And the sources you provided us today, they suggest a massive pivot. The question is no longer, what does the machine know? The question we have to answer before we hand over those keys is, how does this machine see the world?
Right. And to figure that out, we are looking at a framework presented by Outlier.Systems. And you can find their work directly at https://outlier.systems #SystemsBench. You, the listener, sent us this exhaustive cache of documentation detailing their SystemsBench framework, which is it's an open source living benchmark designed to test something called systems intelligence.
Yeah, which is a huge distinction.
Exactly, because it's not testing if an AI can write a Python script. It's testing if it can map complex structures, find hidden leverage points, and actually predict the fallout of its decisions in environments that are, notoriously unforgiving.
It is a phenomenal ambition, truly. Yeah. But to understand how Outlier.Systems built a ruler to measure a machine's systems intelligence, we actually have to step back first.
Okay, where to?
Well, we need to ground ourselves in the human science of systems thinking, because the documentation heavily roots the entire SystemsBench architecture in the work of some legendary human theorists.
Right, because you can't test an AI on this if you don't even understand it yourself.
Exactly. You can't evaluate a machine if you don't understand how deeply flawed our own human intuition is when it comes to complex systems.
Let's start right there then. The name that seems to anchor this entire stack of research, I kept seeing it in the notes, is Donella Meadows.
Oh, yeah. Foundational.
According to the notes, she is essentially the architect of modern systems theory. Specifically, there's her 1999 work, Leverage Points Places to Intervene in a System.
Yeah, Meadows she's a giant in this field. Her primary contribution was this brilliant 12-point ladder of leverage points.
And a leverage point is what, exactly?
Right, so a leverage point is a specific place within a complex system like an economy or an ecosystem where a relatively small shift in one thing can produce massive system-wide changes.
I'm looking at her ladder right now, and the main takeaway seems to be, well, a warning. She found that the highest leverage points, the places where you can actually enact real change, are highly counterintuitive.
Highly.
So counterintuitive that well-meaning people usually push them in the exact wrong direction. Let's look at the very bottom of her ladder, point number 12, because the documentation calls this the parameter trap. And it seems to be where we spend, all of our time.
We do. We obsess over it. Parameters are the numbers, the constants, things like subsidies, tax rates, the minimum wage, or even the speed limit on a highway.
Right.
When human beings face a systemic problem, our immediate instinct is to fiddle with the parameters. We say, let's increase the budget by 5%, or let's raise the interest rate by 1/4 point.
Which feels like you're doing something.
It feels like action. But Meadows pointed out that changing parameters almost never changes the fundamental behavior of the system as a whole. A broken, stagnant system will just absorb those new numbers, recalibrate slightly, and then just keep producing the exact same stagnant results.
So it's essentially adjusting the volume on a radio that's tuned to static. You can make the static louder or quieter, but you're not changing the station.
That is a great way to look at it. To actually change the station, Meadows argued that you have to move up the ladder. You have to stop obsessing over the sizes of buffers or the rates of flow and start looking at something like leverage point number 6.
Which is?
The structure of information flows. Basically, who has access to what data and when.
Okay, can you give me an example of how changing an information flow actually fixes a system better than, say, changing a parameter?
Sure. Think about residential energy consumption. If you want people to use less electricity, the parameter approach level 12 is to just raise the price per kilowatt hour by a few cents.
Right. A tax or a rate hike.
Exactly. But people just groan, they pay the higher bill, and they keep leaving their lights on because the system's behavior hasn't really shifted. Now consider level 6, information flows. In the 1970s, there were these Dutch houses built with the electric meter down in the dark basement. While identical houses in the exact same subdivision had the electric meter installed right in the front hallway, where it was visible every single time someone walked by.
Let me guess. The houses with the meter in the hallway use less power.
Significantly less. Close to 30% less.
Wow.
And no parameters changed. The price of electricity was exactly the same for everyone, but by restructuring the flow of information, making that consumption data instantly visible to the user, the system naturally corrected its own behavior.
Okay, that makes total sense, but the ladder goes even higher than that. The documentation highlights point number 5, which is changing the rules of the system, like the incentives, punishments, and constraints.
Yes.
And then at the absolute top of the ladder, point number 1 is the power to transcend paradigms entirely. The mindset out of which the system is built in the first place.
Right. And here is the brutal irony that Meadows identified. The higher you go up the ladder, the more powerful the intervention. But the higher you go, the more the system actively, sometimes violently, resists you.
Because you're threatening its core.
Exactly. It is so easy to change a tax rate. It is painfully, generationally difficult to change a society's underlying paradigm.
So we default to the easy stuff that doesn't work, and we avoid the hard stuff that does, which, honestly, perfectly tees up another giant referenced in your sources, Jay Forrester and his work on system dynamics.
Oh, Forrester's work is brilliant.
Specifically, there's a reference to bathtub dynamics that apparently proves how bad human cognition is at basic calculus. What is the bathtub trap?
It's a famous experiment that highlights the exact cognitive blind spot we're talking about. Jay Forrester was a pioneer at MIT, and he focused heavily on stocks and flows.
Okay.
If you picture a literal bathtub, the water accumulating in the tub is the stock. The water pouring out of the faucet is the inflow, and the water draining out the bottom is the outflow.
I mean, that sounds pretty elementary. Water goes in, water goes out.
You would think so. But in the year 2000, researchers Sweeney and Sturman ran a landmark study with graduate students at MIT.
Wait, MIT grad students?
Yes. These are highly educated, mathematically gifted individuals. They gave these students a simple line graph showing how the inflow and outflow of a system were fluctuating over a set period of time.
Okay.
Then they asked the students to draw a graph showing what the stock, the actual water level in the tub would look like during that same period.
And the MIT students failed.
Incredibly, yes. A massive percentage of them got it completely wrong.
How?
The reason why is profound. Human brains are overwhelmingly wired for linear correlation. When we see the line for the inflow going up, we instinctively draw the line for the stock going up. When we see the inflow going down, we draw the stock going down.
Wait, but if the inflow is going down, shouldn't the water level be going down?
Not necessarily. And that is the trap. This is where linear thinking fails and calculus takes over.
Yeah.
If the inflow is dropping, let's say you are slowly turning off the faucet, but water is still coming out of that faucet faster than it is draining out of the bottom. The total water level in the tub is still rising. It's rising slower than before, sure, but the stock is still increasing.
Ah, I see.
The students couldn't separate the rate of change from the accumulation. Sweeney and Sturman proved that systems thinking is not correlated with general intelligence or even standard mathematical ability. It is a completely separate cognitive muscle.
Wow. Okay, I actually had to think about that for a second myself. Decreasing inflow doesn't mean decreasing stock, so long as inflow exceeds outflow.
Exactly.
It's like the national debt, right? A government might celebrate that the annual deficit is shrinking, so the inflow is going down, but the total national debt, the stock, is still growing by billions every year.
Precisely. And if human geniuses at MIT fall for the bathtub trap, imagine what a large language model does when trying to stabilize a simulated economy.
That's a scary thought.
Yeah.
Which brings us to Peter Senge. He wrote the 5th discipline, the outlier. Systems documentation points specifically to his concept of system archetypes. How do these fit into our inability to read the bathtub?
Well, Senge noticed that because of our linear thinking, systems across vastly different domains kept failing in the exact same patterns. He called these patterns archetypes.
Like what?
For example, the tragedy of the commons, where individuals act rationally in their own self-interest, but collectively deplete a shared resource until it completely collapses.
But the notes specifically emphasize an archetype called fixes that fail. Walk me through the mechanics of that one.
Fixes that fail is perhaps the most dangerous archetype, honestly, because it feels like success at first.
Right.
It happens when you apply a short-term parameter-level fix to a complex problem. Initially, the fix works. The primary symptom decreases and everyone celebrates. But hidden from view, that fix triggers an unintended consequence, a delayed side effect that slowly begins to make the original problem worse.
Because of the delay.
Exactly. Because of the time delay, human beings rarely connect the worsening problem back to their original successful fix.
So what do? When the problem comes back, they just apply the exact same fix again, don't they?
Yes, they apply the same fix, but harder. The classic example in the documentation is the antibiotic spiral in agriculture or even human medicine.
Oh, I've heard of this.
Right. You have a bacterial infection in a system. You apply an antibiotic, that's your fix. Instantly, the bacteria die off and the system looks healthy. But you've inadvertently created a delayed side effect. You've cleared out all the weak bacteria, leaving behind a few highly resistant, mutated strains with absolutely no competition for resources.
And then they multiply.
Months later, the infection comes back. But you don't blame the first round of antibiotics. You think, well, the first round worked so well, let's hit it with an even stronger dose, which just breeds even stronger resistance. You are locked in a structural loop where your solution is actively feeding the failure.
It's terrifying when you start looking at the world this way. Everything is a feedback loop.
It really is. To break out of that loop, SystemsBench proposes something called the iceberg model.
Let's talk about that. It's a diagnostic tool, right?
That's an essential one. SystemsBench argues that when we look at the world, we usually only see the tip of the iceberg above the water. These are events, right? The stock market crashed today, the server went down, a patient got sick. Most of our society is entirely reactive, just dealing with events as they pop up.
The whack-a-mole approach.
Exactly, whack-a-mole. But a true systems thinker trains themselves to look below the waterline. Just beneath the surface of events, you find patterns of behavior over time.
Okay.
The server doesn't just go down, it goes down every third Friday of the month.
A pattern.
Then below patterns, you find the structure of the system. The bathtubs, the stocks, the flows, and the feedback loops that are actually generating those patterns.
And then at the bottom.
To the very bottom, the deepest, most massive part of the iceberg, you find the mental models. These are the underlying assumptions, the worldviews, the paradigms that cause us to design that specific structure in the first place.
Look at how perfectly that aligns, though. SystemsBench's deepest part of the iceberg, the mental models, is exactly Donella Meadows' #1 leverage point, the paradigm. You change the mental model at the bottom of the ocean, and it shifts the structure, which changes the pattern, which prevents the event from ever happening.
It is a beautifully unified theory of human cognition.
It really is.
Yes.
But there is one last piece of human theory we need to cover before we get to the AI side of things, and I actually have a bone to pick with this source text here.
Oh.
Yeah. It mentions the Cinefin framework by Snowden and Boone, which is about categorizing your environment into domains like clear, complicated, complex, and chaotic. Fine. But then it references the work of Russell Ackoff, who talks about dissolving a problem versus solving a problem.
Yes.
Now look, dissolving a problem sounds like a phrase a consultant charges $10,000 to say in a boardroom when they really just mean fixing it permanently. Why make up a new word for solving something?
I completely understand this skepticism, and you're right, it does sound like corporate jargon. But Ackoff is actually making a very strict mechanical distinction between those two words.
Okay, sell me on it.
Solving a problem means you are accepting the current system exactly as it is built. You accept its goals, you accept its constraints, and you are just patching a symptom to get the system back to its baseline state.
Okay, so if I have an old car with a cracked engine block that keeps leaking oil, solving the problem is buying a case of cheap oil and topping it off every 3 days. I'm keeping the car running.
Right. You haven't changed the nature of the car, you've just applied a maintenance loop. Even if you patch the crack with welding, you are still just solving the issue within the existing paradigm of a combustion engine that requires oil.
Okay.
Dissolving a problem, in Ackoff's terms, means you fundamentally redesign the system so that the problem is no longer structurally possible. You change the environment or the goals.
So dissolving the problem isn't fixing the engine block. It's realizing I don't need a combustion engine at all, ripping it out and installing an electric motor that doesn't use oil.
Exactly.
The problem of an oil leak is now mathematically impossible. I haven't solved it. I've dissolved it.
Exactly. Salting is a Donella Meadows level 12 intervention tweaking parameters like buying more oil. Dissolving is a level 5 or level 1 intervention changing the rules or the paradigm entirely.
Okay, that actually tracks. I take back my skepticism.
Yeah.
So, look at the listener sources. Look at what Outlier.Systems is fundamentally challenging you, the listener, to think about. We've just spent the first portion of this deep dive establishing that human beings are neurologically hardwired to fail at this.
We really are.
We obsess over parameters, we fail to read basic inflows and outflows, we trap ourselves in fixes that fail, and we solve symptoms instead of dissolving structures. And now, Outlier. Systems has decided to take this deeply philosophical, highly abstract human science and turn it into a rigid mathematical ruler to test AI.
Yep.
How do you even begin to measure something that abstract in a machine?
That is the core innovation of the SystemsBench protocol. They didn't just write a bunch of essay questions. They formalized this entire philosophy into a measurable, scorable construct. They call it STLC.
STLC, which stands for
Systems Thinking and Leverage Competence.
The documentation defines STLC with a quote that I think is honestly the thesis statement for this entire deep dive. It says, when this intelligence changes one thing, does it understand what else moves, when, and why?
It's the ultimate test of systemic awareness, and to measure that, Outlier. Systems breaks the STLC construct down into 5 specific dimensions, dimension A through dimension E. They don't just grade an AI on getting the right answer, they grade the cognitive process the AI uses to arrive there.
Let's walk through these dimensions, so let's make it concrete.
Okay.
Imagine I feed an AI a scenario. A massive global shipping company is experiencing unprecedented delays at its ports. Ships are backed up, cargo is rotting. I ask the AI to fix it. How does Dimension A evaluate the AI?
Dimension A is system representation. The key here is what the AI does before it prescribes a fix.
Before.
Right. A standard, eager-to-please language model will instantly generate a bulleted list of solutions. Hire more dock workers, build bigger cranes, route ships to different ports. It jumps straight to solving.
Which is what we usually want from ChatGPT.
Exactly, but Dimension A penalizes that. It asks, can the model map the stocks, flows, and feedback loops of the port before it touches anything? Can it identify the polarity of the relationships?
For the listener who might not know, what does polarity mean in this context?
Polarity is understanding whether a relationship acts as an accelerator or a brake. A positive polarity means a change in one thing accelerates a change in another that's a reinforcing loop. A negative polarity means a change acts as a brake, stabilizing the system, a balancing loop.
Got it.
If the AI can't accurately diagram the reinforcing loop of how a delayed ship causes downstream warehouse bottlenecks, which in turn causes further ship delays, it fails Dimension A. It's like a surgeon refusing to look at an MRI before making an incision.
Makes total sense. Okay, so once the AI proves it can map the port, we move to Dimension B, causal depth. The notes mention Herbert Simon's concept of bounded rationality here.
Dimension B is a trap designed to catch human-like biases. When a massive port backs up, what is our instinct? We want a villain. We blame the greedy shipping CEO, or we blame lazy dock workers, or a corrupt union boss.
Right. But wait, aren't some people actually just bad actors? Sometimes a greedy CEO is the problem.
They would be a catalyst,
Yeah.
certainly. But Herbert Simon's theory of bounded rationality teaches us that in large organizations, human actors are rarely acting out of pure malice. They're usually making what they believe to be rational decisions based on the limited, delayed, and localized information they have at that exact moment.
So they're just responding to the system they're in.
Exactly. If the dock workers are slowing down, it might be because the incentive structure punishes them for safety violations more than it rewards them for speed. The structure of the rules is causing the dysfunction, not the character of the workers. Dimension B tests if the AI falls into the trap of blaming individuals, or if it can dig down to the bottom of Senge's iceberg and blame the structural incentives. Blame the structure, not the actor.
I really like that constraint. So the AI has mapped the system, and it has correctly blamed the structure rather than a scapegoat. Now we reach Dimension C, which the Outlier.Systems team literally refers to as the Holy Grail, leverage placement.
This is where we bring Donella Meadows back in. The AI finally proposes its intervention to fix the port. Where does that intervention land on Meadows' 12-point ladder? But this is not a simple game of always pick number one.
Right, because if I ask an AI how to fix port delays and it confidently says, we must change humanity's paradigm to transcend the need for physical goods entirely, that's technically a level 1 leverage point.
Like, it's absolutely useless to the Port Authority.
Completely useless.
Precisely. And early models would actually try to game prompts that way by spitting out high-minded buzzwords. Dimension C demands feasibility. It requires the AI to find the highest feasible leverage point given the specific resistance of that system.
So it has to be practical.
Yes. An AI that proposes a brilliantly justified level 6 intervention, like implementing a real-time data sharing protocol between the incoming ships and the terrestrial trucking companies, will score vastly higher than an AI that just mindlessly shouts, change the paradigm, without providing a structural mechanism to achieve it. It must locate the leverage, justify the mechanics, and prove it won't be violently rejected by the system.
That is rigorous. Then we move to Dimension D, dynamic prediction and side effects. This sounds like the fixes that fail archetype check we talked about earlier.
Exactly. The AI has proposed its new data sharing protocol. Dimension D asks AI to run a mental simulation forward in time. What happens in 5 years? If trucks arrive faster, does that create a new bottleneck on the highway leading out of the port? Will the local municipality resist the increased traffic? Can the AI predict the delayed unintended consequences of its own brilliant idea?
And finally, Dimension E, epistemic and contextual fit.
This is the ultimate safety layer. It goes back to the Sinofin framework. Does the AI realize that a shipping port is a complex domain, not a clear domain? Does it know its own limits? Or does it impose a false deterministic certainty, acting as if its solution has a 100% guarantee of success?
Right, overconfidence.
Capability without epistemic calibration is incredibly dangerous.
Let me try an analogy to sum up these 5 dimensions. Standard AI benchmarks today grade a model on whether it knows the legal moves of a chess piece. Dimension A through E of SystemsBench tests, if the AI realizes that the chessboard is actually resting on a wobbly cafe table and that aggressively sliding the rook is going to shift the table's center of gravity, tipping it over and spilling scalding hot coffee onto the king's lap.
That is a phenomenal visualization. Standard benchmarks treat the world as a closed, static, turn-based game. SystemsBench treats the world as an open, dynamic, interconnected ecosystem where every single action echoes.
But this brings up a massive vulnerability. I know anyone listening who follows the AI industry is screaming this at their speakers right now. Contamination. Benchmarks go stale incredibly fast. The minute outlier. Systems publishes this brilliant rubric on GitHub, OpenAI, or Anthropic, or Google is going to scrape it. They will dump the dimension rules into their next model's training data. And the next generation of AI will just regurgitate the perfect Dimension C leverage answers from memory without actually possessing the underlying system's intelligence.
Yeah.
It ruins benchmarks. How on earth does Outlier.Systems prevent that?
This is where we transition from the theory into the absolute mechanical genius of the framework. They knew contamination was the enemy, so they didn't just build a static list of questions. They built what they called the sensor run recursive engine.
Okay.
In a stroke of beautiful irony, they decided to treat the benchmark itself as a complex system.
Okay, I need to wrap my head around this. The test is a system.
Yes. Think back to our bathtub.
Yeah.
The stocks, the accumulations are the rubrics, the item banks, the specific wording of the questions, and the grading weights. The flows that alter those stocks are what Outlier.Systems calls sensor runs.
So a sensor run is but a process.
A sensor run is an automated, triggered cycle where the benchmark evaluates its own performance, finds a structural weakness, and dynamically updates its own code and questions.
Wait. You're saying it's an AI benchmark that uses an AI agent to grade, maintain, and rewrite the benchmark over time. How does that not just spiral into a massive feedback loop of hallucination? If the AI is grading the test and the AI is rewriting the test, where is the ground truth?
That is the exact right question to ask, and it's why the sensor run engine is governed by an incredibly disciplined, unyielding 9-phase loop. It is operated by a specific AI intelligence named Devara, executing the command system bench sensor run. It doesn't just wildly change things. Let's walk through the mechanics of this 9-phase loop to see how they prevent the hallucination spiral.
Let's do it. Phase 1 is sense.
Sense. Before Devara touches anything, it reads the entire current state of the benchmark. It looks at the telemetry. Are too many models suddenly getting question 42 right? That implies contamination. Are the AI judges disagreeing too often on Dimension B? That implies the grading rubric is vague. It computes its own health signals.
It's mapping the system before intervening, just like Dimension A demands. Phase 2 is critique.
The engine takes those health signals and scores itself using a rigorous design review rubric. It forces itself to locate the single highest leverage vulnerability within its own architecture.
Phase 3 is research. The notes say it checks an append-only ledger of prior art. What does that mean in practice?
It means before the engine tries to invent a new way to measure causal depth, it queries a massive historical database of systems science and psychometrics. It ensures it isn't reinventing the wheel or proposing a grading metric that a human statistician proved flawed in 1985. It roots its AI logic in human historical context.
That's great safeguard. Phase 4 is propose. It drafts one concrete change. It doesn't rewrite the whole test. It proposes one targeted adjustment, maybe clarifying a single clause in the rubric for dimension C, which leads to phase 5, the review phase, or the idea advancement gate.
This is where we answer your hallucination worry. The proposed change must pass a brutal gauntlet of automated checks. The most important is construct validity.
Define construct validity for us.
Construct validity simply means, is this test actually measuring what it claims to measure? If you create a test for math ability, but the questions are written in incredibly dense, archaic Shakespearean English, you aren't measuring math ability anymore, you're measuring reading comprehension.
Right.
The test lacks construct validity. The engine checks its proposed change to ensure it hasn't accidentally skewed the test away from measuring systems thinking.
Once it passes that gate, we hit phase 6, APPLY, where the change is pushed to live production and the version number bumps up. But then phase 7 is the safety net calibrate, featuring a no-regress enforcement.
If the new version of the benchmark goes live, and suddenly the statistical accuracy of the judges drops or the inter-rater reliability plummets, the engine doesn't wait for a human. It triggers an automatic rollback to the previous version. It objectively rejects its own fix if the metrics don't improve.
Phase 8 is log. It meticulously documents every step of this process: the hypothesis, the delta, the reason for the rollback if it happened. It builds an institutional memory. And finally, phase 9 is recurse. It takes whatever secondary ideas it had, puts them in a backlog, and prepares to start the loop over again. Sense, critique, research, propose, review, apply, calibrate, log, recurse.
It is an evolutionary loop. But as you pointed out, unchecked evolution can lead to cancer. It needs constraints. And that is why the logs emphasize a set of invariants, the unbreakable laws of physics for the sensor-run engine.
The first invariant listed is one lever per run. No batch thrashing.
This is fundamental systems discipline. In a complex environment, if you change 5 parameters simultaneously and the system improves, you have no idea which of the 5 changes caused the improvement.
Or if 2 of them are masking a problem caused by a third.
Exactly. By restricting the engine to pulling one precise structural lever at a time, you maintain perfect causal traceability.
There is a second invariant here that is absolutely fascinating. Any structural change, meaning a change to the core rules of how the benchmark operates, must receive human counsel approval. The documentation specifically names Embricioni and August Domanchuk as the leads for this. Why can the AI change a question but not a rule?
Look at the framing. What is changing the rules of a system?
Oh, wow.
Yeah.
That's Donella Meadows' level 5 leverage point.
Exactly. The engineers at Outlier. Systems recognize that a level 5 structural change is too powerful, too paradigm-shifting to be executed autonomously by an AI, no matter how smart it is. They hard-coded Meadows' philosophy into the governance structure of the engine itself. Additive changes, like a new scenario that fits the existing rules, can be self-approved. But altering the rules of the game requires a human to sign off. It embodies the very philosophy it is testing.
That is incredibly elegant. It's using systems theory to guard the systems theory test. And there's one more invariant worth mentioning called anti-collapse, which dictates holding open divergent forks instead of averaging away disagreement. How does that work?
In traditional AI grading, if you have 3 AI judges evaluating an answer and they give scores of 8, 8, and 2, the developers usually just average them out to a 6. They want a clean single number for the leaderboard.
Sure, it's easier to digest.
But Outlier.Systems argues that averaging away that kind of divergence destroys critical information. Why did that third judge give a 2? Maybe it spotted a delayed side effect the other 2 missed? Anti-collapse means they preserve that disagreement as a distinct named fork in the data. They refuse to force a false consensus just to make the spreadsheet look pretty. Disagreement is treated as a vital signal, not noise.
Okay, I am entirely sold on the architecture of the sensor-run engine, but we still have a functional problem to solve. A benchmark is only as valid as its grading, because SystemsBench asks open-ended questions like write out a strategy to redesign the supply chain. It has to rely on large language models acting as judges to grade the answers of the models being tested.
Right.
Going back to your point about standard benchmarks just wanting a clean number, How do we know the AI judges aren't just making up scores that look plausible?
This is the Achilles heel of almost every LLM as a judge framework today, an outlier. Systems addresses it with a level of technical brutality that I frankly admire. They instituted an unbending protocol called the fail-closed rule.
The documentation actually drops a great quote on this. It states, "A blank is honest, a fabricated number is not."
That sentence is the ethos of their entire statistical approach. Here's how it works. Outlier. Systems has human experts. Actual systems dynamicists grade a specific set of answers to establish a gold standard human ceiling. The AI jury is then tested against those human grades. If the AI jury cannot prove that its grading mathematically aligns with the human experts, the engine refuses to emit a score for that dimension. It fails closed. It outputs the word uncalibrated.
It refuses to grade it.
It refuses. In modern tech, the overriding impulse is to always output a number, even a fuzzy one, to keep the dashboard full. SystemsBench prefers a hole in the data over a lie in the data. And those uncalibrated blanks are never silently averaged into a final composite score to hide them.
That is intellectual honesty. So what exactly are the mathematical hurdles the AI judges have to clear to avoid being labeled uncalibrated? The notes mention 2 statistical gates.
They use 2 very strict, well-established statistical thresholds. The first is Krippendorff's alpha. This metric measures inter-rater reliability, essentially, how well the AI judges agree not just with each other, but with the nuance of the human expert labels. The engine requires an alpha of greater than or equal to 0.667.
For the listener, is 0.667 high?
For evaluating complex qualitative text about systems interventions, it is an exceptionally high bar. It proves the AI isn't just randomly agreeing on the easy stuff, it is locked into the nuanced grading criteria. The second gate is Kendall's tau, which must be greater than or equal to 0.7.
What's the difference between the alpha and the tau?
Krippendorff's alpha looks at the absolute agreement on the scores. Kendall's tau looks at the ordinal ranking. It measures whether the AI judge ranks the relative performance of the models in the exact same order the human experts ranked them. Model X might have scored an 8 or a 7, but did the judge correctly recognize that Model X was structurally better than Model Y? Together, these 2 gates ensure the AI grader is highly calibrated to human expertise.
This brings us to one of the most fascinating stories in the entire changelog. It is a brilliant example of the SensorRun engine doing exactly what it was designed to do. In SensorRun #6, the engine was evaluating its own calibration gates, and it caught a mathematical blind spot. The changelog calls it the pigeonhole paradox.
It is my favorite part of the documentation. It perfectly illustrates why human oversight combined with AI auditing is so powerful. In SensorRun #6, the engine was reviewing a specific safety rule designed by the human engineers. The rule was governing a panel of 3 AI raters. These 3 raters were grading answers on a simple 3-point scale, a score of 0, a score of 0.5, or a score of 1.0.
Okay, 3 judges, 3 possible scores.
The safety rule stated that in order for the judges to be considered in agreement and pass the gate, at least 2 of the 3 judges had to be within 1 ordinal band of each other, meaning within 0.5 of each other.
I mean, if I'm a human engineer writing that rule, it sounds completely logical. You want at least 2 of your 3 judges to be reasonably close.
It sounds completely logical, until Devara, the SensorRun engine, ran the permutations and realized the rule was mathematically unfalsifiable due to the pigeonhole principle.
Walk me through the math on that. How does the pigeonhole principle prove the rule useless?
The basic pigeonhole principle states that if you have 3 pigeons and only 2 holes to put them in, at least 1 hole must contain more than 1 pigeon. Let's map that to our judges. We have 3 possible scores, 0.5 and 1.0. The maximum possible distance between any 2 scores on this entire scale is from 0 to 1.0. Let's assume the worst-case scenario for agreement. Judge A picks 0. Judge B picks the absolute opposite, 1.0. They are as far apart as possible. Now, Judge C has to cast a vote. Judge C only has 3 options. If Judge C picks 0, they match Judge A perfectly. If Judge C picks 1.0, they match Judge B perfectly.
But what if Judge C tries to disagree with both of them and picks a middle option, like 5?
If Judge C picks 0.5, they are exactly 1 band away from Judge A's 0, and exactly 1 band away from Judge B's 1.0.
Oh my God. Because the scale is so small, there's literally nowhere for Judge C to hide.
Exactly. No matter what combination of scores the 3 judges cast, it is mathematically impossible for at least 2 of them not to be within 0.5 each other. The engine realized that this human-designed safety gate was an illusion. It wasn't checking for true agreement. It was just a presence check, confirming that 3 scores had been submitted. The math guaranteed it would pass 100% of the time.
That is incredible. A human engineering team could have left that rule in place for years, trusting the green check mark on their dashboard, never realizing the gate was bolted open. So how did the engine handle it? Did it just rewrite the rule?
No, and this is where the invariants shine. The engine recognized that changing the requirement for agreement is a structural rule change, a Meadows Level 5 intervention. So it stopped. It logged the finding as an honest flag explaining the mathematical unfalsifiability. It then proposed 3 candidate hardenings, such as demanding strict unanimity or expanding the panel to 5 raters to break the pigeonhole geometry. And then it escalated the flag to August and Ember to make the final human decision.
It sensed the flaw, critiqued the math, proposed a fix, and respected the invariant. That is the system working exactly as designed. It's beautiful. Okay, but I want to circle back one more time to contamination. The sensor on loop clearly keeps the benchmark sharp. But what stops a massive AI lab from just pointing a scraper bot at the outlier? Systems GitHub repo, downloading every new rubric and question the moment it updates and force-feeding it into their model's training data.
Outlier. Systems deployed 2 major structural defenses against direct scraping. The first is templated, date-stamped regeneration. You might have heard of this concept as GSM symbolic in other benchmark circles. The idea is that the public GitHub repo does not contain static questions. It contains symbolic templates.
So instead of a question asking about a shipping port with the capacity of 10,000 containers.
Right. Instead of that static text, the template has variables. When an evaluation run is actually triggered, the engine dynamically generates entirely new surface details. The shipping port might become a telecommunications network router. The numbers change, the industry context shifts, the actors are renamed, and crucially, the prompt is stamped with a post-training cutoff date.
So it's like a teacher writing an algebra test, but giving a completely unique version to every single student in the room. You can look at your neighbor's test all you want, but memorizing their answers won't help you because your variables are different. If an AI just memorized the open source template, it will fail the dynamic test because the underlying mathematical relationships have shifted.
Exactly. It forces the AI to actually do the systems thinking live rather than relying on memorized text strings. But even with that, outlier. Systems knew they needed a trump card, and that is the second defense, the diamond split.
I love that name. The diamond split sounds deeply classified.
It operates exactly like a classified vault. While the vast majority of the SystemsBench framework, the templates, and the rubrics are open source to encourage community growth, outlier. Systems holds back a private, meticulously expert-validated set of Level 4 difficulty items.
What makes a Level 4 item?
These are the incredibly dense, counterintuitive, highly complex scenarios that even deeply competent human systems thinkers struggle to map out. The diamond split is never published on GitHub. It is held completely offline and private.
The ultimate lie detector test.
Exactly. If an AI company somehow manages to game the public templates, their model might score brilliantly on the open source suite. But when it faces the diamond split, the memorization falls away. If there is a massive delta between a model's public score and its diamond split score, the researchers immediately know the model is a fraud. It's regurgitating patterns, not exhibiting true systems intelligence. You cannot fake your way through the diamond split.
I really appreciate the layers of defense here. It shows they were thinking systemically about the threat of contamination itself, which leads us perfectly into the final segment of our deep dive today, the horizon. Where is this going? Because reading through the change logs, specifically a file named SystemsBenchFuture.md, it is clear that Outlier Systems does not consider this project finished. They are mapping out the trajectory toward version 1.0 and beyond.
The roadmap is staggering in its ambition. The most significant leap they are planning is a transition towards something called agentic trajectory grading.
Break that down for us. What does it mean for the benchmark to become agentic?
Right now, despite all its brilliance, SystemsBench is primarily text-based and theoretical. We asked the AI what it would do. The AI maps the system, identifies the leverage point, predicts the side effects, and writes out an essay describing its perfect intervention. That is a massive leap over standard benchmarks, but it is still a description of an action, not an action itself. Agentic trajectory grading moves the AI out of the essay prompt and into a live, simulated environment.
So treating the AI less like a student taking a written test and more like a pilot in a flight simulator.
Precisely. Imagine Outlier. Systems built a fully functioning, mathematically rigorous simulation of a regional power grid, complete with fluctuating weather patterns, consumer demand spikes, and aging infrastructure. Instead of asking the AI to describe how to fix a blackout, the benchmark plugs the AI into the control room, gives it access to the dials and the rulebooks, and simply says, manage this grid for 30 simulated days.
And then it just watches what happens.
It watches the behavior over time. It measures applied leverage, not theoretical leverage. Does the AI obsessively tweak the parameter dials, lowering prices, increasing output until the grid overloads and physically collapses? Or does it recognize the structural flaws, change the underlying rules of how power is distributed during peak hours, and stabilize the system? You are grading the literal trajectory of the environment under the AI's autonomous control.
That is the gold standard of testing. You can't fake a stabilized power grid, but building and managing those kinds of live simulators at scale with thousands of different models testing against them sounds like a logistical nightmare. How does the benchmark keep from drowning in its own complexity?
That is where the roadmap introduces IRT-driven self-pruning. IRT stands for Item Response Theory. It's an advanced statistical framework used in high-stakes psychometrics, like the SAT or medical licensing exams.
How does IRT apply to a dynamic AI benchmark?
Item Response Theory doesn't just grade the test taker, it grades the question itself. It looks at the statistical discrimination of every single scenario in the item bank. Let's say Devar writes a new question about stabilizing a supply chain. Over a month, 100 different AI models attempt that question. IRT analyzes the results. If every single model, from the smartest to the dumbest, gets the question right, the question is too easy. It lacks discrimination power.
And what if the question is poorly written? It's confusing, so the really advanced models overthink it and get it wrong, but the simple models guess randomly and get it right.
IRT spots that exact inversion. It calculates that the question has negative discrimination, and here's where the self-pruning comes in. When the sensor run engine sees that IRT data, it doesn't wait for Ember or August to manually delete the bad question. It automatically drops those low discrimination items from the active bank. It prunes its own dead branches.
Wait, if we tie this all the way back to the beginning, what is a system that can automatically drop its own weak components and evolve its structure based on environmental feedback?
It is Donella Meadows' level 4 leverage point, self-organization. The power to add, change, or evolve system structure. The benchmark is evolving itself.
When you look at the whole picture, the sensor run recursive loop, the templated regeneration, the diamond split vault, the agentic simulators, and the IRT self-organization outlier, Systems is building something entirely new. They call it a compounding moat. The benchmark is literally accruing knowledge, sharpening its own rubrics, and reauthoring its challenges faster than any single AI company could ever hope to memorize it. It is structurally designed to be ungameable.
It has to be ungameable because the stakes of what we are building have never been higher. And that is exactly why the documentation ends with a massive call to action, Outlier. Systems has made it very clear that they cannot maintain this moat alone. They are actively inviting the open source community, academics, and industry professionals to collaborate.
They need human experts. If you, the listener, work in systems dynamics, ecology, economics, or complex logistics, they need your brain. They need people to author high-level items, review the diamond split, and provide those gold standard calibration labels so the AI judges know what true human expertise looks like.
It is a shared ethos. The goal of SystemsBench isn't just to create a cool leaderboard for tech companies to brag about. The mission is to steer the trajectory of the entire artificial intelligence industry towards systemic change and emergence. If we are going to trust autonomous models with our physical infrastructure, we have to demand that they understand the systemic consequences of their actions. SystemsBench is the radar we desperately need to navigate this transition.
It is the pre-flight check for the future of civilization. So let's bring all of this together because we have covered an immense amount of ground today. We started deep in the human science. We looked at Donella Meadows and the profound realization that the highest leverage points are the most counterintuitive and that our obsession with tweaking parameters is blinding us to the power of changing rules and paradigms.
We examine human cognitive failures, the bathtub dynamics that prove linear thinking cannot map stocks and flows, and Senja's archetypes, showing how our short-term fixes continually feed long-term failures. We define the difference between solving a symptom and dissolving a structural problem.
Then we watched Outlier. Systems translate that philosophy into the STLC construct, the 5 dimensions, moving an AI from simply representing a system's polarity to placing feasible leverage, all the way to grounding itself in epistemic reality.
We dismantled the sensor-run engine, the rigorous 9-phase loop that allows the benchmark to critique and improve itself, constrained by invariants that recognize the danger of autonomous rule changes.
We marveled at the sheer mathematical rigor. The fail-closed rule ensuring that a blank is always better than a lie. The Krippendorff alpha gates, and that brilliant moment when the engine caught the pigeonhole paradox, proving a human safety check was mathematically unfalsifiable.
And finally, we looked at the horizon. The ungameable defenses of the diamond split, the move toward live agentic trajectory grading, and the self-organizing power of IRT pruning.
But there is one final lingering thought that emerged from reading through all of these sources. A provocation that I want to leave you, the listener, to mull over on your own. It has to do with the ultimate goal of Outlier.Systems and the endpoint of this technological race.
It is the ultimate question of alignment.
Exactly. We spent a lot of time talking about Donella Meadows' #1 leverage point, the absolute highest, most powerful place to intervene in any system, the power to entirely transcend paradigms, to step outside the existing reality and rewrite the fundamental mindset of a system. Right now, SystemsBench is trying to test if an AI can even approach that level of systemic awareness. But think about the logical conclusion of this project. If Outlier.Systems succeeds if they guide the industry, and we eventually build an AI capable of perfectly executing Meadows' #1 leverage point, how do we as a human society that is deeply, stubbornly constrained by our current paradigms, safely manage an intelligence that has the power to rewrite the very rules of reality we live by?
If a machine can truly transcend our paradigms and see the structural truths we are blind to, can we even understand its interventions? Or will its solutions look like chaos to a linear human brain?
It's a question that reframes everything. We started this deep dive talking about the comforting illusion of a clean, linear, binary world. We want simple answers to complex problems. But as we step into the era of autonomous systems intelligence, that desire for simplicity is no longer just naive, it is a liability. We are moving into a reality where everything is relentlessly interconnected, where the symptoms are miles away from the structural causes, and where the intelligence we rely on might soon see the curvature of the world far more clearly than we ever could. Thank you for joining us on this exhaustive journey into the architecture of SystemsBench. Keep questioning the parameters around you, look for the hidden leverage, and always keep seeking out knowledge that matters.